Thank you very much, and thank you for the invitation to come here and speak to you all today. I'm normally based in Dublin, in Ireland, but I do get over to the US quite a bit to visit, mainly New York and Chicago, where Corvil has offices. The fresh air of Colorado makes a welcome change. So I'm delighted to be here. I'm going to tell you a bit about our story. We've been a Napatech user for quite a long time, almost 10 years now. I'm going to tell you a bit about where we come from, where we started off, focusing on the electronic trading space, which is really where we got our start. And the folks in electronic trading are very big users of time-stamped network data. So I think it will be interesting for you to hear about some of the things that they do with time-stamped network data, and also where we see that sector going in the future. So electronic trading, this is maybe a 50,000-foot view of what electronic trading looks like for those of you who may not be familiar with the space. So in this very simplified diagram, over on the left-hand side, you have the exchanges, the markets where trades actually happen. On the right-hand side, you have the traders, so the trading firms who are actually listening to market data, responding to what they see in market data, and sending orders into the markets. And then in the middle, you have the brokers who are routing those orders to markets on behalf of the trading companies, and also the market data services, which is an entire sub-industry in its own right involved with consolidating, processing, and distributing market data. So what we do in this space, we have customers in pretty much every segment of the industry. And what we do is we focus on, first of all, performance monitoring, client experience, so helping these firms to understand the experience that their clients are getting from their systems. We have quite a few use cases as well around compliance and technology risk. So all of the firms in this space are subject to a lot of compliance rules, as you can imagine. And they also are quite keen to avoid things going wrong with their technology. There have been several incidents where firms have lost a lot of money because their technology infrastructure started to misbehave or go rogue. And finally, a relatively new space for us, cybersecurity, making sure that these systems are secure from attack. So let me just talk a little bit about performance, first of all. So in the electronic trading space, performance really means latency. That is what people are most concerned about, making sure that their orders get into the market ahead of everybody else's, that they are the fastest to respond to a change in market conditions, and so on. This chart here just gives an impression of how latency has changed over the years within the electronic trading space. So what it's showing is exchange order response times. So the order response time at an exchange is from the time that I send an order into the exchange to the time that I get a response back again from the exchange telling me that they've received my order. How long does that take? And this chart shows data points taken from a bunch of different exchanges over the years. So you can see back in 2006, 10 milliseconds was not a bad place to be for responding to customer orders at an exchange. But today, that latency has come right down to the 10 to 100 microsecond range. So they've got a heck of a lot faster. The latency is actually halved every 18 months or so over this time frame. The y-axis there is logarithmic. So that straight line that you can see drawn through the data there represents an exponential rate of decay. And what it tells you is that latency is coming down by about a factor of 2 every 18 months. I think more recently it may have started to flatten off a little bit, just as a lot of companies have started to bump up against the very limits of what can be done with software. Quite a few firms, of course, are using hardware acceleration now as well in order to meet these very stringent latency requirements. So these latencies are incredibly short, and as you can see, in order to monitor and measure those latencies accurately, you're going to need something that goes quite a bit beyond what software is capable of. So software generally is not really capable of measuring latencies reliably in the microsecond range. So as well as that, we've seen an enormous increase in data volumes within the electronic trading industry. This chart here is showing the peak messages per second seen in the Oprah data feed, which is one of the big financial data feeds over the years. So as you can see, it's been increasing at an exponential rate. This only goes up to 2015, unfortunately, when it was just over 10 million messages per second in the Opera data feed. And of course, that has happened because as systems have become more automated, people are trading faster and faster. They're also trading in smaller increments. So automation means that it is much less expensive nowadays to generate and process individual orders in the markets than it used to be in the past. And so people have taken advantage of that to split large orders up into ever smaller increments, larger and larger numbers of small orders. And so the message rate has just gone up and up and up. All of these orders generate many messages. And interestingly enough, while data volumes have grown continuously over time, the intraday variability within these environments in the message rate that you see there is quite extreme as well. So not only are data volumes going up all the time, they're also extremely bursty. So as you can see in this chart here, which was taken from a typical brokerage environment, in the morning, there's a huge burst of activity when the market's open. In the evening time or in the afternoon when the market's closed, there's another huge burst of activity. But during the day, the activity rate is generally much lower. There may be spikes of activity due to market-moving events, such as a change in interest rates at the Federal Reserve, for example. But the peak-to-mean ratio that we see in second-level message rates would typically be well over 100 to 1. Ratios of 1,000 to 1 are not unusual. So what do we do within this environment? Well, first of all, to accurately measure those very short latencies that our customers are interested in, precision timestamps that are able to generate accurate sub-microsecond results are very important to us. And that is one of the big advantages that packet data provides to our users within these environments. So hardware timestamped packet data enables them to get access to extremely accurate timestamps that they can use to measure very short latencies accurately. The packet data also provides a couple of other advantages. So first of all, packet data allows you to measure latency between well-defined, unambiguous monitoring points. So many firms will instrument the edge of their systems. They will look at packets coming into their network and packets leaving their network. And that enables them to get a true end-to-end, wire-to-wire measurement of performance right across their system. And it also means that there are no question marks over where those latencies and where those timestamps are coming from. If you're doing that in software, then there often is a question mark over exactly what those latencies represent. And finally, packet data is a non-intrusive way to monitor these systems. So it doesn't put any extra load on the servers themselves, the production servers that are actually carrying out critical trading tasks. All of that workload can be offloaded to a separate system. And that's quite important when you're trying to monitor these extremely large message rates. So we provide appliances that enable our customers to realize these advantages. And of course, as part of that appliance, we make use of specialized monitoring NICs that provide us with precision hardware timestamping. There's a couple of other features there that are also quite important to us. So the ability to synchronize accurately with external time using protocols such as PDP or PPS That is very important because, of course, NTP sync does not provide anything near the level of accuracy that our customers would need. The ability to keep up with those extremely large traffic rates, and especially the burst of activity when the market suddenly becomes very active, that's very important to us. And of course, the ability to capture all of that data with zero packet loss, so making sure that we can capture absolutely everything. Generally, our customers want to monitor and capture records for every single thing that happens within their networks. They're not particularly interested in sampling. They're certainly not interested in randomly losing selected packets from the data flow. And there's good reasons for that. So compliance is important to them. And a lot of this data that they're capturing is ultimately used for compliance purposes. So you have to have a record of everything. They also use it to respond to their own clients. So if their own clients may have queries about what happened to a particular order that they sent in at 10 microseconds past 9 a.m. this morning. And if you want to answer that question, you need to be able to find that order in the packet data. So you can't afford to have randomly discarded it due to an overloaded monitoring system. So as I mentioned, we've been an Apotec user for quite a long time to deliver this capability. So I would like to say thank you to Napatech for providing such excellent monitoring NICs to us, and also for the excellent customer support that they have provided to us over many years. We've never encountered a difficult problem that we've not been able to solve with the help of the Napatech team. So thank you for that. So measuring latency that these environments, it does introduce quite a few challenges. I want to talk about just a couple of those and some innovative ways that we solve them. So first of all, these systems are generally highly distributed. So most of our customers trade across multiple markets. They have systems that are co-located in many different trading data centers. And so that means that they need to be able to measure latency between different places. It's not possible to get all the measurements required on a single appliance. You need something that will work in a distributed environment. And that, of course, means that you need the ability to track packets and messages as they travel from place to place. So the appliances that we deploy will continuously exchange information between themselves about what they can see on the network. We do that by generating signatures for each network packet or application level message that we see, and streaming those signatures continuously between the different monitoring points where we expect the packets to show up. You also have to deal with the issue of clock sync, of course. So if you're measuring in different places using different clocks, you need to make sure that those clocks are synchronized. And the most accurate way to do this, of course, is using PPS or PTP. NTP isn't good enough, as I mentioned. We have, in the early days, most of our customers didn't have access to good clock sync infrastructure. It's actually non-trivial to build out a high-quality PTP delivery system and network. It takes a bit of time and effort and expertise to do that. And in the early days, most of our customers didn't have it. It's gotten a lot better since then. So a lot of the trading data centers nowadays will have access to pretty good clock sync feeds. But we still find plenty of places where customers just don't have access to that. But they still need to be able to accurately measure latency. So one of the things that we did, we developed our own self-sync technology to generate accurate latency measurements, even when you don't have external sync. And the way that we do that, the appliances will continually exchange timestamps read from, for example, the Napatech card, to tell each other what time they currently think it is. But we actually leave the clocks free running in that mode. So it actually just acts as a pretty accurate time counter. But the actual reading has no relation to real-world time. We leave it free running because that's the most stable mode of operation, because what the appliances are actually doing in this scenario, they're building up models of each other's clocks. So in software, we continually track the offset between all of the clocks, and we keep a record of that, we're able to model the drift over time due to temperature changes and other effects which can change clock frequency. And what that means then is that when we need to generate a latency measurement, each appliance is able to look up and calculate an accurate offset between its own clock and the remote clock at the time that the remote timestamp was made. And in that way, you're able to get a pretty accurate latency reading. So we found that with this approach, you can measure latencies that are accurate to within microseconds, which is quite a bit better than what NTP, for example, would provide. So a good NTP implementation would typically give you accuracy to within maybe a bit less than a millisecond. But this approach, which just produces latency measurements and doesn't synchronize clocks to external time, can accurately measure latencies in the microsecond range. Of course, to get down to the sub-microsecond range, then you do need to use PPS or PTP. So another challenge that we faced is that our customers generally are not only interested in network latency. So they don't want to just measure the latency that network packets experience as they move from place to place. They're actually most interested in application layer latency. So they want to know how long it takes for their various application components to process the messages that they're handling. So this diagram shows a simple example of that. We have a trader who is sending an order to a broker in the middle, and that broker is forwarding the order on to an external exchange. So the broker order is actually a separate message. It's a different message from the message that the trading firm sent in. So to understand the relationship between them, you need to be able to gain access to the application layer message and the identifiers that are inside those messages. You can't do it just by looking at network packets. And similarly, once the order is forwarded from the broker onto an external market, you'll then get a response back. That response may contain new identifiers, and ultimately that generates a response going back to the original trader who generated the order. So what's happening here is that messages are coming in, new messages are being generated based on those client messages, and the identifiers that can be used to track those messages are changing all the time. So to measure latency within this system, to measure, for example, how long it takes the broker to process that incoming order from the client and generate the order that they send out to the exchange, you need to be able to decode all of that application layer data that's contained inside the packets. And you also need to be able to handle the various transformations that occur with the identifiers that uniquely identify those different orders. So that led us to implement message layer, application layer decoding for all of the network data that we process. Today we have about 800 different decoders that we use to analyze trading data and to extract the application layer data from the network packets that we see. So this is just a very simple example, schematic really, of what the decoded data inside those application layer messages typically looks like. So we can see we've got timestamps, first of all. We can see that there's various different message types involved here: orders, trades, cancel requests. We can see the identifiers that uniquely identify those orders in terms of their ID and the firm that generated them. So those identifiers are critical then to being able to understand latency at the application layer within these environments. But interestingly enough, once you decode this data, you can see that there's quite a lot of business relevant information in here as well. So the way that we do this is that we decode all of the application layer content. We don't just decode the parts that we need for latency measurements, typically because you never know in advance what is actually going to end up being useful. So we decode everything that we see. And that ends up exposing quite a lot of information that's pretty interesting from a business point of view. So we can see which stocks are being traded. We can see the prices that they're being traded at, the sizes of the various orders that are being placed. So again, this is a very simple schematic illustration. Typically, these messages would have dozens or hundreds of fields, all of which would be exposed by our appliance. So what does that enable you to do? So first of all, it enables you to generate performance measurements in terms that are of most interest to our clients. So for example, it allows us to track those orders as they move through complex systems and to tell them about things like average order to book latency. So from the time that we send in an order to the time that that order gets placed into the order book at an exchange, how long does that take? Other interesting measurements would include cancel to out latency. So from the time that someone asks for an order to be canceled, how long does it take before the order is actually canceled? But it also enables us to go quite a bit beyond that in terms of showing people what the business outcomes currently, what the business conditions currently are within their infrastructure in terms of the percentage of their orders that are being filled, the volume of trades that are actually occurring, and the amount of money that's changing hands. And those metrics actually end up being quite important to our clients as well. So of course, if you're a trader, then you will have lots of systems that are able to tell you how much trading you're currently doing and how much money you're making. But what our customers really wanted to see is that they wanted to be able to see infrastructure metrics such as latency side by side with the current status of their business. So they wanted to be able to ask questions like, if server XYZ within my infrastructure is running slow right now, which clients are affected by that? How many orders are being affected by that? And also the other way around, if my latency is currently going up because of a problem within my network routing infrastructure, is that having an effect on the volume of orders that are being sent to me by my clients? Are they sending their orders somewhere else now? So they wanted to be able to see business metrics like this side by side with latency so that they can understand the relationship between infrastructure performance and what's happening in their business. So I think that it's an early example of something that may become more common in other industries because, of course, more and more industries are becoming highly automated. They're relying on automated systems, not just to process their business data, but to actually make business decisions in real time. And once you have that level of dependency on your infrastructure, then it becomes more important to you to be able to see my infrastructure performance and my business performance side by side so that I can see what the relationship is between them and whether there is any impact. So of course, that's going down that route. Every business is different. Even within the financial trading space, there are many, many different business models. So people want to be able to see this type of data in different ways. The view that is critical to one particular trader, a high-frequency trading firm, may be much less important if you're a broker. If you're a broker, you have lots of clients. You're most interested in what's happening to my clients. Are they getting a good experience? If you're a high-frequency trader, you don't have any clients. You only care about, are your orders getting executed successfully in the market? So everybody wants to see this type of data differently. And so you end up with a bit of a challenge in terms of being able to provide all of these different views to different customers. There are quite a lot of different metrics that we produce natively within our product itself. But we found that our customers want to be able to slice and dice this data in many different ways and generate their own perspectives on the data that we are producing. So we came under a lot of pressure to provide bespoke advanced analytics, allow people to run their own analytics on the data that we produce, to create their own custom visualizations. And of course, our customers also want to store a lot of this data long-term for compliance use cases. So the data that we produce is very useful for that because it is so accurately time-stamped. You've got these incredibly accurate timestamps associated directly with order and trade events. And that's exactly what regulators in the financial trading industry are increasingly asking trading firms to provide, because the regulators want to be able to reconstruct the precise sequence of events whenever anything goes wrong in the market. But the regulators typically want our customers to store that data for 5 years, 7 years. Their timescales are very long, and obviously that's a lot more data than you can fit into the appliance model that we currently provide. So to solve some of these issues, what we started to do is to essentially to stream our data, the data that we produce, out to external systems, and to integrate with more third-party systems that give people more flexibility in terms of the ways in which they use it. So we take the data that we produce, we allow our customers to normalize it directly on our appliance, and then we stream it live to external big data stores and third-party systems. So Splunk, for example, very popular with a lot of our customers. A lot of them use it for IT ops. It's becoming a single entry point for people looking at data from not just the network, but also from logs and from servers and so on. So that's a very popular destination for the type of data that we produce. But we also have customers who want to scale to much larger scales than Splunk can easily do. So we integrate with systems such as Kafka, such as big data stores. There are also some specialized financial database systems such as KDB that are often used as destinations for this type of data. So just to give you a flavor of the type of architecture that a serious user might deploy in order to consume this data and provide the various different analytics that they want to look at. This is an example architecture based on a project that we did with the customer a couple of years back now. It isn't necessarily, some of the choices here are not necessarily the ones that I would recommend nowadays, but I think the main functions, it does work to illustrate the main functions that the architecture provides. So over there on the left, we've got a bunch of Corvil appliances that are listening to network data, getting those accurate timestamps, decoding the data from the wire, and then streaming the results of that into a big data system, using Kafka as a message bus to receive that data and to distribute it across multiple systems, using, for example, Spark as a real-time processing engine to generate additional analytics or to do advanced machine learning on that data as it comes in. And then storing that data in big data stores, which can give you that long-term retention that you may need for compliance use cases, for example. And then, of course, you need a self-service visualization layer on top of that that allows you to create your own dashboards, to slice and dice the data in different ways, and to generate the views that you want to use. So I think certainly the Kafka and Spark, they end up being very good choices here for receiving that data, for distributing it across multiple systems, and for giving you the power to process large amounts of data in real time. And so this then is the type of view that a customer might generate based on that data. So you can see we're looking at things such as the worst 5 clients by latency down here at the right. But we can also see business metrics such as fill rate, for example, would be a very important metric for a lot of our customers. So that's the percentage of your orders that are successfully getting filled in the markets. And generally speaking, if you're too slow, then your fill rate will go down. So being able to see that side by side with latency becomes very important. But to be honest, the specifics that are shown here are not the key thing behind this. The important thing is that this view becomes something that our customers can create by themselves. So they have the flexibility to create these dashboards themselves. And sitting behind it, they have a big data platform that gives them the power to slice and dice the data in pretty much any way that they want, and to get that custom visualization that they were demanding. So let me just check how I'm doing on time. Okay, not too bad. So as we were doing all of this work with data analytics to help our customers access the data that we produce in more flexible ways, the industry was also becoming more concerned about security. So let me say a little bit about that. Of course, security has always been a major concern for the financial industry. Financial firms come under attack all of the time from people who are motivated by desire for financial gain, or who are motivated by political activism. More recently, there has also been a worry that they could come under attack because, of course, the financial markets are a critical part of national economic infrastructure. So any major disruption in the financial markets could cause economic chaos. And so the regulators have become increasingly concerned just in the past couple of years to make sure that the markets are safe from cyber attack. So the head of the Federal Reserve, the head of the SEC recently called this out as their top concern for the industry today. And shortly after she did, it emerged that the SEC themselves had come under cyber attack and had been breached about a year ago by people who are looking to try to gain access to corporate filings ahead of the rest of the market. So it's the kind of thing that goes on all the time. So traditionally, the financial industry has relied on perimeter defenses to keep out cyber attackers. So especially in the financial trading space, these systems have a very, very well-defended perimeter. A lot of these systems, there is no connectivity to the internet, no direct connectivity to the internet from anywhere within the trading infrastructure itself. And they're very tightly locked down with access control lists and so on. So the systems that are allowed to connect, that are allowed to access the trading infrastructure are very tightly controlled. But of course, the perimeter defense model is no longer regarded as sufficient within the wider cybersecurity sector. It's recognized nowadays that insider attacks are actually the preferred mode of attack for hackers today. So something like 80% of cyber attacks today are insider attacks. So they may be attacks by employees, disgruntled employees, such as the incident shown on this slide, but more commonly they are attacks carried out by gaining access to employees' login credentials, and then being able to bypass the perimeter and access these systems, pretending to be an employee. So our customers started to ask us, well, we have a lot of Corvil network monitoring technology deployed within this trading infrastructure, so can we start to use that to monitor for insider threats? This is what the infrastructure typically looks like within, for example, a brokerage trading firm. So there are a couple of different parts to the environment. So at the top right here, we can see the trading network where most of the production traffic is passing back and forth. At the top in the middle there, you can see the clients who are sending orders in to the broker. On the right, we have the exchanges. And then we have a management network that the brokerage employees use to manage the production environment. So what's important here is that we have a production network with a pretty tightly defended perimeter. But we also have connections to partner firms, we have connections to clients, we have connections to exchanges. In terms of the actual traffic flows within this environment, typically there will be quite a lot of market data flowing from the exchanges, being consumed by the brokers' order processing systems. So those data flows are largely unidirectional, multicast market data. Connectivity only occurs in one direction. And they use quite a lot of exchange-specific data protocols to distribute that data. We'll also have order flow. So these are the network flows that the clients are using to place orders with the brokerage and that the brokerage is using to forward those orders on to external exchanges. So these are unicast data flows. They're bidirectional. Information flows in both directions. And again, there's a bunch of specific protocols that are typically used within the environment to exchange that data. And then we also have the management traffic. So where the brokerage employees are accessing the systems in order to manage them. They may have some form of remote access as well via some encrypted VPN. So in terms of the vulnerabilities within these systems, there's a couple of things that a trading firm like this would typically be worried about. First of all, they'll be worried about insider attacks, so employee credentials, people accessing our systems pretending to be an employee. They may also be worried about disgruntled insiders, employees who try to steal data or software from the environment itself. They also regularly come under quite a bit of denial of service activity on any internet-facing systems that they may have. As well as their employees, they'll also be worried about their partners. So could something go wrong with some of our trading clients? They have connections with us to place orders with us. What could go wrong there? And they may also be worried about their exchange or external market partners as well. They usually have systems co-located with all of the exchanges, so that physical environment is not directly controlled by the trading firm themselves. They're relying on somebody else to make sure that they are physically secure in those deployments. So in terms of looking at this environment, obviously the trading network at the top right is very important, but the management network at the bottom is also of high importance. Most of the data flowing there will be using various different enterprise protocols. So we actually have quite a high level of support for enterprise protocols as well as trading protocols. We do the same thing for enterprise protocols that we do with trading. We decode all of the data that they contain, and we expose that data, we publish it. And we have quite a wide range of coverage. So our customers were interested in what we might be able to do to help them secure these environments. And over the past couple of years, this has become an increasingly important use case for us. There's a couple of different techniques that we now deploy on our appliances to help out with security. So, I mean, generally speaking, if you look at the security space, the set of techniques that are used fall into a couple of categories. So first of all, there are techniques based on known attack patterns, so based on looking for known signatures or known indicators of compromise that can occur within network data. I know Suricata are here today, that they're obviously well known for being very good at doing that. Then at the top right, threat intelligence, so receiving information from threat intelligence feeds about known malicious servers that are out there on the internet. And that also helps to keep up to date with the set of known threats that are out there today. But of course, people also worry about the set of threats that are not known today. They worry about things that haven't been discovered yet, for which there is no detection signature, and which have not yet been called out in any of the threat intelligence feeds that you can access. And so that's where techniques like machine learning are becoming increasingly important. And they basically work by trying to spot things that are different, that are unusual, potentially threatening things that have suddenly appeared within a network environment where previously they didn't exist. So just as an aside on machine learning, this chart here shows the Gartner 2016 hype cycle. I'm sure it's a chart that many of you are familiar with. So Gartner, the technology analysts, produce this chart every year. It basically shows the current marketing status of a bunch of different technologies that are out there. They believe that technologies go through this natural life cycle where they start with some innovation trigger, they move on to the peak of inflated expectations, then they go down into the so-called trough of disillusionment, before finally coming back up again on the slope of enlightenment. So if you're wondering where machine learning currently is on this chart, we're right there at the top of the peak of inflated expectations. Mind you, this was from 2016, so we may be heading down just a little bit into the trough of disillusionment at this point. There are definitely challenges in applying machine learning to network data. The environments are exceptionally diverse and dynamic. So everybody, I think, who's worked with network data at any time will know that. There's a lot of change within the data that we see over time. And that happens for a couple of different reasons. So first of all, data is dynamic over time because it reflects what's happening within the infrastructure, and IT teams tend to be constantly changing the infrastructure around, moving applications from one place to another, moving services from one place to another, setting up new servers, new machines, adding employees to the company or taking them away. So there's a constant pace of change and what you see in the network reflects all of that. There's also a lot of change because a lot of network technologies are inherently dynamic nowadays. So there's an inherent level of dynamism that you can see in dynamically managed environments. Network data is also very diverse across different firms. So because it's becoming increasingly integrated into the actual business that firms are doing, the type of network data and the patterns that you'll see in different firms can be very different. It reflects the way that they actually do business. And that means that what you learn from one environment may not necessarily be applicable to another environment. And so this has led to a certain level of criticism that machine learning for security use cases can generate a high rate of false positives when applied naively, if you like, to network data. And when you look at security use cases, the fact is that false positives and false negatives both have a very high cost. So a false negative means that you didn't detect a breach that you perhaps should have detected. So that obviously has a cost. But false positives also have a cost because they take time to investigate. So every false positive that you detect is going to send an analyst, a skilled employee, off on a potential wild goose chase. And so false positives also have high costs. And part of the reason for that is that network data, as we know, it's quite low level. The anomalies detected in network data are often difficult to interpret at a higher level. When you try to understand which user account, for example, may have been associated with an anomaly, that's not always easy to infer. It takes time, it takes work, it takes energy to figure that out. So one of the things that our customers told us is that, yes, there is a high rate of change within our general enterprise environments, but our production systems in the trading world are very tightly locked down. The pace of change there is very low, and we don't use dynamic technologies, we don't use virtualization a lot, we don't use anything that could add latency to our production environment. And things that are dynamic generally do add some level of latency. So our customers were pretty confident that their production environments are extremely stable. And in fact, they wanted us to alert them on any change that we found there whatsoever. and investigating that, it did turn out that there is definitely truth in that that assumption that many of our customers were making. Here's just an example. So if you look at the set of hosts that you see within a traffic set over time, if you're looking at internet traffic, you'll see a picture that looks like this. So on the x-axis, we have the number of days that we've been monitoring this traffic set. And on the y-axis, we have the number of unique hosts that we have seen there so far. So of course, if you're looking at internet traffic, that number is just going to go up and up and up all the time. Every day, people in a corporate environment may be looking at different websites. They may be accessing different servers out there on the internet. So the number of hosts that you see is just going to keep going up over time. If you look at a general enterprise environment, just looking at traffic within the enterprise, the picture is a bit different. So it's a little bit more stable. So we can see here, after 150 days of monitoring, for this particular environment, we start to see the number of hosts that have been seen start to level off. So it's a bit more stable, but it's still quite dynamic, and that's just because general enterprise environments change an awful lot over time. But looking at a trading production environment, we actually end up seeing quite a different sort of a picture. So the number of hosts that you might see within the network traffic, you actually learn the identity of most of the hosts within this environment pretty quickly. And after that, the pace of change is actually much slower. And each change that you see over time after the initial learning period will basically be the onboarding of a new client or moving a system from one exchange co-location point to another point. So they're pretty significant changes. So what we've actually done for our trading customers, we've implemented a security model that basically exploits stability monitoring to try and figure out which parts of the infrastructure that we're deployed in are actually stable and which are dynamic over time, which are changing, and which parts we can expect to remain stable as we continue monitoring. So when it's deployed in a brokerage environment like this, then of course what you'd expect to see is that any internet connectivity is going to be highly unstable. The enterprise environment itself will be quite variable, but the production environment will show up as being quite a stable environment. And so in that environment, it starts to make sense to alert on the different anomalies that we can see there. So we deploy statistical anomaly detection algorithms to monitor the set of hosts that we can see, the set of applications that are running on those hosts, and also the set of connections that they make to each other and to external systems. And once we've got that monitoring in place, we then learn over time which parts of the environment are stable and which parts are quite dynamic. So for the stable part of the infrastructure, we will then start to call out anomalies whenever we see any unexpected changes. So making use of this in practice, of course, depends on successfully identifying a substantial part of the production environment as being actually stable. It's worked out pretty well for us so far within the trading vertical specifically. So it does turn out that most of their critical infrastructure shows up as being stable under one or more of these different dimensions once we start analyzing it. So then we produce results in a security report, which would look, for example, like this. So we'd be calling out connectivity anomalies, changes in the patterns of connectivity between different machines, or unusual applications running on production servers. We combine all of that with traditional signature-based detection and with threat intelligence to produce an overall risk score. And then we present the results on a per host or a per user basis. So I haven't explained very much about the per user aspect here, but basically we correlate this information with user authentication data that we get from decoding Kerberos traffic, for example, in order to figure out which users are associated with each of these events. So in that way, we generate risk scores for users and for hosts. And so that gives people a pretty high-level view into the riskiest hosts and users within their environment. And we also provide the backup detail around what we've seen for each individual host or user so that they can quickly identify what exactly is going on here. So we produced this for the data on individual CNEs individual appliances directly on the appliance itself. We also take the data from the appliances into Spark-based clusters to produce these types of reports for larger infrastructures. So I'll need to stop there. So just to summarize, I hope that I've been able to convey the value that our customers in electronic trading get from timestamps, network data, both for traditional use cases such as performance monitoring, but also for new use cases such as cybersecurity, and also some of the directions that we are currently going with our customers as we develop further technologies, architectures, and use cases. I think we've managed to get to perhaps 10% of the value that timestamped packet data can actually provide for these users. And we're busy trying to fill in the remaining 90%. So, thank you very much.
Any questions?
So for the essentially protocol analysis or decoding you do, is that all custom in-house software, or do you use something like Bro or Suricata to do the base heavy lifting?
So, me personally, or the
Corvil software?
Corvil.
Yeah.
So we sell the appliance as our main product. So that is it's a standard server appliance with the specialized monitoring NIC in there as well. It has our software loaded onto it. Most of our customers would take that as a hardware appliance. We do have a virtualized model, virtualized implementation as well. But certainly most of our electronic trading customers would take that as a hardware appliance. Any other questions?
Does your company do the application level diagnostic with that method you're talking about? I mean, considering variety of applications, and how did you differentiate them to do?
In terms of decoding the actual application data?
Yes.
So we use a plugin model for that. So we have software plugins for specific protocol families or specific applications that are able to decode the network data in real time. So we've got many hundreds of those now. So it's done in software.
For the network anomaly detection, what kind of data set you supervise, unsupervised? What kind of algorithm did you use to do the anomaly detection?
So at the moment, we're using primarily statistical anomaly detection. So in other words, we have a statistical model of the patterns of change that we see within the environment that we're monitoring. And we are identifying statistical anomalies based on that model. And we then combine all of those models together to produce a risk score. So there's a scoring function that will take in detections from multiple different detectors, statistical anomaly detection, signature-based detection, and threat intelligence-based detection as well, and combine those together to form an overall risk score. So that risk scoring function, at the moment, that is primarily engineered by us based on our experience so far with data in the field.
In your algorithm, is there any room for the user to input their weights, their specialties?
So that is a very interesting question. So I think there is some evidence out there that when you incorporate user feedback directly into these security systems, so in other words, if you have a skilled analyst who is looking at all of the data that you produce and who is then providing an indication of, yes, this was a threat, or no, that was not a threat, and when you incorporate that feedback directly into your learning model, that can actually improve the performance of models quite a bit within any particular specific environment. So it's a very interesting approach to do that. The challenge, of course, is that you need, at the moment, it seems that you need a skilled security analyst who is willing to spend the time to actually go and investigate each one of these anomalies and to train the model for the specific environment that you're looking at. So at the moment, we don't do that. It's very interesting to think about whether there's a way to make that scale well.
Thank you.
Okay, thank you very much.